Now we're going to find the work done to lift the Red Bull Stratos capsule to the altitude of 120,000 feet where Baumgartner jumped. So I suggest you watch the jump video before this one so you know what's happening. The altitude of the jump was 120,000 feet, which I used my meter to foot conversion I got on the internet after Googling that, and that's how many meters it is. And the weight of the capsule, they told us on the website that it was 2,900 pounds, so that's this many kilograms. The work is being done by the air pressure to fill in under the balloon as it rises, because helium, it's a helium balloon, is lighter than air. Okay, so work is defined as force times distance. So you're fighting against a force and you're moving at a distance, you're doing some work. So that's a good definition. The gravitational force that we're interested in this particular problem is at a distance r from the center of the Earth, is this formula right here. So capital G is a gravitational constant and has units that we'll discuss below. And the mass of the Earth is this many kilograms, and the little m mass of the capsule is this many kilograms. Now notice in this formula, this r squared is in the denominator. So that means the farther you are from the center of the Earth, the less the gravity, or the force due to the gravity of the Earth is. So in other words, the force diminishes. So as the capsule rises, the force on it due to the Earth will diminish, but it'll be a very gradual process. So the force is changing. The distance from the center of the Earth to the surface, in other words, the radius of the Earth, is given to be this number, that many meters. And I wanted to check that. I got interested in seeing, in the metric system, gravity is supposed to be, acceleration due to gravity is supposed to be 9.8 meters per second squared. So I wanted to see if mass times that would be the result if we plugged it into this force formula, using that the r was on the actual surface of the Earth, so this was the surface. So I plugged all the numbers in, and sure enough, everything came out to be 9.8 times the mass that we already had. That's exactly what it's supposed to be. Now going back to our problem. The capsule is to be lifted from the surface of the Earth up to 36,576 meters further than the surface of the Earth. So you add those two. I factored out at 10 to the 6, moved the decimal place over so that I could just add them in terms of 10 to the 6. And this is how many meters it is. 6.43 something times 10 to the 6 meters. So the capsule is being lifted, and all the while the force on it is diminishing. But the force at a certain radius is only good right at that radius. So this is where our calculus comes in. At a distance r from the center of the Earth, that's here, we can say that the force at that radius, which is this quantity, is good for a small delta r distance further out. So it's good up until here. And then the next value of r takes over, which is a farther out number. So the work to move the capsule from r out to the r plus delta r location is a force times the distance. And so here's a force times that distance it's traveling, delta r. So the total work is to add up all those tiny works along the journey as your radius steadily increases as your capsule gets lifted by the balloon upward. So it's summing all those from the surface of the air out to the final destination altitude, and so that turns into the integral that we have there. And I factored out all these constants. I'm not going to deal with those numbers until I need to. This is a very simple, one of the simplest integrals to do that you'll see in the class. It's r to the negative 2 raised the exponent by 1, r to the negative 1 over negative 1. Then I took the negative 1 out to here. I have the 10 to the 6th, those numbers down in the bottom because it's 1 over r. I factored out a 10 to the negative 6 to be multiplied in the numerator here. Did these two on a calculator, got this answer inside there for the subtraction of fractions, and you still have your 10 to the negative 6. Then I'm just writing down again our constants, what they are, as a reminder, so we can plug them in. We're plugging them in. The negatives canceled out. The 8.8 is here. The negative 4 plus the negative 6 is the negative 10. And I have all the other constants. There's G, there's the capital M, Earth's mass. Here's the capsule's mass. Multiply it all together, and you get this number here, which is in kilograms meters per second squared. That's the force. So that's a force times the distance is meters. But this force is also called newtons in the metric system, times the meters. And newtons times meters is further reduced and called joules. Joules of work in the metric system. Then I put that into my joules and foot-pound converter that I found online, and this is how many foot-pounds it is. So that's a lot of work being done to raise that capsule, and yet there's no rocket. It's just the fact that the helium is lighter than the air, and that's what's doing it. However, when you do finally reach the final destination, you don't drift off into space because the density of the air is so small that it equals the helium. So you just start floating there and you don't go any higher.